intramolecular forces are the forces within a molecule. So this would be a covalent bond, or between ionic bonds, those are intramolecular forces within, while inter, like an interstate, goes between molecules. So this would be an intermolecular force, while that, again, was an intramolecular. So intermolecular forces are just attractions between molecules, while intra are the bonds that are within it. Ionic bonding is a special case, though, because its intramolecular forces are the same as its intermolecular forces. So it's the same force between the ions as within the bond. So we have an intramolecular ionic bond, and we also have intermolecular ionic bonds. For ionic bonding, strength is determined by two things. The charge of the ions. The higher the charge, the stronger that attraction will be. And then size of ions. The smaller the ions are, the closer they can get to each other, which makes a stronger attraction. We look at charge first. If the charges are the same, then we'll look at size. Whichever one is smaller will be stronger. If you recall, size increases as we go to the left and down. Left as we have less protons, and down as we have more energy levels. So if we want the smallest size, we want the one that's further up and to the right. Let's look at our first example. First, we look at charges. Calcium is a +2 charge. Chlorine is a -1 charge. Iron, we can't tell because it has a variable charge, but we know that chlorine is a -1, and there's 3 of them, so that's a -3, so iron must be a +3. We're doing the absolute value of that, so 2 times 1 is 2, and 3 times 1 is 3. 3 is a bigger charge than 2, so iron 3 chloride has a stronger attraction than calcium chloride. Go ahead and figure out your charges for B. Restart when you're done. So 2 times 2 should have given you a 4, and a 3 times 1 should give you a 3. So magnesium sulfide has a stronger bond than aluminum chloride. Looking at C, we have a +1 -2 and a +1 -2. Notice that our charges are the same. Since our charges are the same, we're going to look at the size of the atoms. We have cesium and lithium and oxygen over here. We wanted smaller size. Well, they both have oxygen, but lithium is much smaller than cesium. So lithium oxide, we would expect to have a stronger ionic bond than cesium oxide. Go ahead and do that last one on your own. Restart when you're done. You see the charges are the same. They both have K, but fluorine is much smaller than bromine. So Kf, we would expect to have a stronger ionic bond. Here's another example of inter and intramolecular forces. Notice that we have intermolecular forces holding the 2 molecules together, while all these single and double bonds are all intramolecular covalent bonds. When a substance undergoes boiling or melting, we're weakening and breaking the intermolecular attractions. We're not breaking the covalent bonds. There's 5 types of intermolecular forces that we're going to be talking about. Ion-dipoles, dipole-dipole, hydrogen bonding, dipole-induced dipole, and London dispersion forces. The first one is dipole-dipole. Dipole, we remember from our bonding unit, meant that it was polar. 2 poles. So we have a slightly positive side and a slightly negative side. So dipole-dipole attractions are interactions between molecules with a dipole, aka that are polar. So polar molecule with another polar molecule. The positive end of one molecule is going to be attracted to the negative end of another polar molecule. They arrange themselves where we have attractions and repulsions. Two positives are going to repel each other, keeping them spaced, while a positive and negative will attract. For dipole-dipole attractions, their attraction depends on two things. One, smaller size. The smaller the molecules are, or smaller the atoms in the molecule are, the closer they can get to each other. And for molecules that are approximately the same size, we're going to look at electronegativity. The higher the electronegativity difference, the more polar it is, the stronger the attraction. Remember that for electronegativity, the further up and to the right it was, the more electronegative it was. So first we look at size, and then if they're roughly the same size, we want the more electronegative one. So for HBr and HCl, they both have hydrogen. They're both polar because there's just one bond, and that bond is of different elements. So that electronegativity difference would be greater than 0.4. We have Br and Cl. We said we wanted the smaller atoms so the molecules can get closer together. So HCl is smaller than HBr, so we would expect it to have a stronger dipole attraction. Go ahead and pause the video and do B on your own. Restart when you're done. Both of these are also polar, as they have lone pairs on the central atom. Se is smaller than Te, so we would expect H2Se to have a stronger dipole-dipole attraction. And finally, looking at this picture, circle the dipole-dipole attraction on your note page. If you circle that, you are correct. Remember that this is what breaks when HCl vaporizes, not the bond between H and Cl. Hydrogen bonds are not a bond. Even though the name says hydrogen bond, it is still just an attraction. It's actually an extreme form of dipole-dipole attractions because we still have two polar molecules attracted to each other. Specifically, though, it's the attraction of a hydrogen in one polar molecule attracted to an N, O, or F of another polar molecule. So this is what we see in water. So this is a hydrogen bond. Notice that it's the hydrogen of one water is attracted to the oxygen of another water molecule. It can also be between different molecules. Here we have ethanol. So this is ethanol. And ethanol is attracted to water molecules in hydrogen bonding. So this oxygen is attracted to the hydrogen of the ethanol. And then this hydrogen is attracted to the oxygen of ethanol. So that's a hydrogen bond, and that's a hydrogen bond. Notice that it's still just attractions. Why hydrogen bonds are so much stronger than a regular dipole-dipole is because we had just said that dipole-dipole wants small atoms and large electronegativity differences. Well, nitrogen, oxygen, fluorine, and hydrogen are all very, very small atoms, which allows the dipoles to get very close to each other, strengthening that attraction. N, O, and F are also very electronegative, which means that when they combine with hydrogen, it's going to make a very polar bond. So the two things that we said makes dipole-dipole attraction stronger, hydrogen bonds just are the extreme example of them. They're the smallest atoms and the most polar bonds. Looking at this list of 8, figure out which of these can form hydrogen bond attractions. So HBr, it does have hydrogen, but it doesn't have N, O, or F. So HBr cannot form hydrogen bond attractions with itself. H2S also cannot form hydrogen bonds with itself because we don't have N, O, or F. N and O are both atoms that can form hydrogen bonds, but again, it needs a hydrogen to be able to form a hydrogen bond with itself. NAF is ionic, so that takes it off. HF, we have hydrogen, and we have a fluorine. So HF can form hydrogen bonds with itself. NH3, we have N and H, so again, that can form hydrogen bonds with itself. Water can form hydrogen bonds with itself. And C and H is nonpolar, first off, so there's no way that that could form hydrogen bonds with itself. And there's no N, O, or F. Some of these molecules could form hydrogen bonds with the circled atoms, but they couldn't form hydrogen bonds with themselves. The next intermolecular force is London dispersion forces. London dispersion forces are found between all covalent molecules, but they're the only force of attraction between nonpolar molecules. London dispersion forces are caused by the motion of electrons. Electrons are in a constant state of motion. So when two nonpolar atoms or molecules approach each other, the attractions or repulsions between the electrons can lead to the distortion in their electron clouds. The more electrons it has, the higher the chance it has of having one of these momentary dipoles. So let's say that we had 4 electrons over here and 4 electrons in this one. When atom A gets close to atom B, so the electrons are constantly moving, sometimes though, one side gets more electrons than the other side. So this side now becomes slightly positive, and this side becomes slightly negative. So when it approaches on atom B, the electrons in this one are going to be repelled, making this side slightly positive, this side slightly negative, which then induces the next atom next to it, and so on and so on. So the strength of London forces is due to the following factors. More electrons. More electrons is going to lead to a higher London dispersion force. And remember that it's because those electrons are constantly moving. The more electrons you have, the greater chance you have for one side to have more than the other. This is what we call polarizability. Polarizability is the ability for a molecule to exhibit a momentary dipole due to one side having more electrons than the other. So first, let's just figure out which one of these can only form London dispersion forces. So we're looking for which one are nonpolar. If it's nonpolar, it can only form London dispersion attractions. So HCl, you have one bond and it's different elements, so that's polar. This one is CH. We could draw it out. When you have more than one central atom like this, all of them are going to count as the center atom, so we have the same thing all the way around. So this is nonpolar. Since it's nonpolar, it can only form hydrogen dispersion forces. You may want to make note that if it's CH and only C and H, if it's only C something, H something, it must be nonpolar. Therefore, will form LDF or London dispersion attractions. pH3, if we draw that out, we'll see that it has a lone pair. Since it has a lone pair, it's polar. It can form stronger attractions than London. Br2, we have one bond, and that bond is both bromine, so that's an electronegativity difference of 0, so that's nonpolar. So Br2 can only form London dispersion attractions. If you have just a noble gas will share, it doesn't share its electrons, and so that will only form London dispersion attractions. And we've seen water earlier, but water has lone pairs, so again, it's not going to be nonpolar. All the ones I X'd out can form London dispersion forces, and they do form London dispersion forces. Just the ones that are circled can only form London dispersion attractions because they're nonpolar. So these 4 molecules, and atoms can only form London dispersion forces, so figure out which would have stronger London forces in each pair. Restart when you finish A. We're not looking at valence electrons, we're looking at total electrons. So helium has 2 electrons, and argon has 18, the same as its atomic number. So argon has stronger London forces. For the bottom one, we can just look at it and tell which one has more electrons, but bromine has 35 electrons and carbon has 6. But there's 4 bromines, while for this one, carbon has 6 and each hydrogen only has 1. So that means CBr4, or carbon tetrabromide, must have stronger London forces than CH4. You wouldn't normally need to calculate it, but if they were too close and you had to calculate it, that's how you would calculate it. Each bromine times the number of valence electron or total electrons that it has. Ion dipole forces are between 2 different molecules. All the ones we've seen before, I can have a bunch of water and they're going to form hydrogen bonds between them. Or if I have helium, a container of helium, they're going to form London dispersion forces between the helium atoms. But for this one, it has to be 2 different molecules. What that means is it's going to say sodium chloride in H2O, bromine ions in H2O, HF mixed with magnesium chloride, sodium chloride and H2O. It's got to say 2 different molecules. One's going to be ionic and the other one's going to be polar. Ion, ionic, dipole, polar, so ionic, polar forces. Ion dipoles are super important because this is how all salts or ionic compounds dissolve in water or any polar compound. So when you drop sodium chloride in water, the negative ion or chloride would be surrounded by waters. Notice all of the hydrogen atoms are facing the chloride because hydrogen is slightly positive. And then all of the positive ion of the salt, such as sodium, is going to be surrounded by the the oxygen side of water because oxygen is slightly negative. This keeps the sodium and chloride, or whatever the positive and negative ions, from going back together. Dipole-induced dipole also must be between 2 different molecules. But this one is dipole, so a polar molecule is inducing a polar in something that doesn't normally have a polar. So this is nonpolar. So it must be between a polar molecule and a nonpolar molecule. So here we have oxygen. Oxygen is nonpolar. Then we have water, which has a permanent dipole because it's always polar. As the water gets brought near the oxygen, just like in a London dispersion, it causes this oxygen to get distorted, and it induces a dipole on that oxygen. As this slightly negative oxygen comes near the oxygen, the electrons go away from it, making it slightly positive, and the other side slightly negative. Polar molecules can induce or create a dipole in molecules that don't have a permanent dipole. That's what's occurring here. So our examples, we have bromine mixed in with water, so 2 different substances. HCl in C6H6. Or in the picture, oxygen and water mixed together. So 2 different molecules. You have this in your notes. What you need to add to your notes is we're going to say ionic bonding is the strongest and London dispersion is the weakest. That is definitely not true. Some London dispersion forces are actually stronger than even hydrogen bonding. But without more information, we're not going to be able to tell that. We'll see more about that in our next video, which is properties. Without more information, though, we're going to say ionic is the strongest, then ion dipole, hydrogen, dipole-dipole, dipole-induced, and London dispersion for the weakest. To figure out what type of attractions you have, the first thing you want to ask yourself is there an ionic compound? We know it's ionic because it's going to start with a metal or ammonium ion. If you see an ionic compound, then it's got to either be ionic or ionic dipole. Do you have polar molecules and ionic present? Then it can be ion-dipole, because remember, ion-dipole had to be two different molecules. While if you don't have two different molecules, it's just going to be ionic. If it's not ionic, you say, well, do you have polar molecules? If you don't have polar molecules, it's got to be London dispersion. It's got to be nonpolar. If you do have polar, well, do you have polar and nonpolar? If so, it's dipole-induced. And if not, you say, do you have hydrogen attached to N, O, or F? If so, it's hydrogen. If not, it's just regular dipole-dipole. So go ahead and pause the video and figure out which force is in these six. Restart when you're done. I've also listed the abbreviations that we'll be using for each of the intermolecular forces in class. So if you want, you can use the abbreviation. Just make sure you know which one stands for which. So oxygen is nonpolar. It's the same atoms attached to each other. So that would be LDF. Here we have a nonpolar and a polar substance. Nonpolar and polar will be dipole-induced dipole. We don't have to draw this one, but if you were to draw it, you would see that you have three elements, or two different elements attached to the central atom. Anytime you have different atoms on central atom, it's got to be polar. So I know it's one of these two, but I don't have hydrogen attached to N, O, or F, so that's just regular dipole-dipole. For this next one, we have a large carbon chain with oxygens coming off, and then an O and an H. You don't have to draw that out. If you see a carbon chain ending in OH or COOH, that's going to be hydrogen bonding each time because that O is attached to the H. And you have more than two elements, so it's going to be polar. For CCl4, you have carbon with 4 chlorines coming off. So same thing all the way around, which makes it nonpolar. And if it's just nonpolar, it's going to be LDF. And then the last one, we have KBr. K is a metal, so this is ionic. And then water is polar. So this would be an ion-dipole. Go ahead and pause the video and figure out which of these interact primarily through London dispersion forces. In other words, we're looking for the one that's nonpolar. This one has 3 different elements. So that one would not be London. That would actually be dipole-dipole. H2S, without drawing it, I know that there has to be lone pairs on sulfur because hydrogen can't double bond. So this one also has to be polar. It's dipole-dipole. And at this point, we could draw those out. I know that B, though, never double bonds, and it only really ever gets 6, so this one is nonpolar. And then my sulfur dioxide does have a lone pair on this sulfur, so this one would also be dipole-dipole. So if you said B, you were correct. We're going to rank these in order of increasing intermolecular forces. So what you're going to want to do is figure out what intermolecular force is in each of them, and then rank them. We want increasing, so we want weakest to strongest. Restart when you're done. We saw on the previous page, sulfur dioxide had a lone pair, so it was dipole-dipole. We also saw methanol previously, or one similar to it. It ends in OH, and it's a hydrocarbon, so that would be hydrogen bonding. And helium is a noble gas. All your noble gases are going to be LDF, or nonpolar. The weakest is going to be LDF, so C and D are out, because helium is our LDF. Hydrogen is going to be our strongest. So if you said A, you are correct. You'll definitely be given pictures and asked which of these represents hydrogen bonding or draw the picture. So look at these pictures and figure out which one represents how methanol, which is CH3OH, would hydrogen bond with itself. So A has two hydrogens attracted to each other, so that can't be happening. D also has two hydrogens attracted to each other, so that's not a hydrogen bond. So it's between B and C. So what you have to look at is on this first one, you have an H attracted to an O and an H attracted to an O in both cases, but that H is attached to a C. So the H is attached to a C and it's attracted to the O. Same thing on this side. This hydrogen right here would not be slightly positive because this is not a polar bond. The only place that methanol is polar is the O and the H area. So here we have a slightly negative O attracted to a slightly positive H. So C is our answer. So it's got to be an H attached to an NO or F, attracted to an NO or F. So here our H is attached to an O and it's attracted to an O. This H is attached to a C and it's attracted to an O. So that one wouldn't be a hydrogen bond. So draw a diagram to represent how hydrogen bonding would occur between HF and water. Restart when you're done. So you could have had the H of water attracted to the fluorine like that. So that would be a hydrogen bond. Or you could have had the O attracted to the H in HF, and that would also be a hydrogen bond. So hydrogen is slightly positive, F is slightly negative, and it should be attracted to the slightly negative oxygen, and fluorine should be attracted to a slightly positive hydrogen.